Okay, now the recording has started. We just got started. Problem 2 in section 2.1. Okay. What are your guys' thoughts? Is the average rate of change going to be positive, negative, from 3 to 7?
Negative.
Why do you think that?
Because from 3 to 7 on the graph, like right in that section, like you can see it going down, like the.
Mm-hmm.
And
okay. That's a very good point. But we're actually, the question is asking us to differentiate between the average rate of change and the instantaneous rate of change. It should just be 0. I don't know why I wrote neutral. So basically, the way that I think about this is if I'm looking for an average rate of change, I look for a line. So here is where my x equals 3 and my x equals 7. And it wants me to like figure out like what the change is between x equals 3 and x equals 7. So the average rate of change is actually just the line connecting these two. Because from 3 to 7, it goes through this change. Okay. That being said, this average rate of change here would be positive because this is a positive slope. All right. Then we have to consider the instantaneous rate of change, which is what's happening directly at 3. And so the instantaneous rate of change at 3 is the line is going down, or the curve is going down. So it would be negative at 3. And so that's just like, this problem is just kind of like meant to like make you think about what the difference is between average and instantaneous so that you can like differentiate that in future problems. Do you guys understand this concept? Like, as far as like telling the difference between average and instantaneous? No one's saying anything?
Instantaneous is the change at that specific moment, whereas average is the change between two intervals. And
yes.
B would be F. That's where the F prime kicks in, right?
Yeah.
Okay.
So F prime is just one way of saying derivative.
Derivative. Okay.
And so we would say that the derivative, which is the derivative equals the instantaneous rate of change. And yes, Casey, you're also right. The instantaneous rate of change is like a zoomed up version of like average rate of change. The instantaneous rate of change is some way that I think about it is, okay, so like what's the difference between f of 3 and f of 3.0001? And then it just keeps getting progressively smaller and smaller and smaller and smaller and smaller, like the distance between 3 and 3.001. So conceptually, it basically is like, did you guys talk about limits? Sorry, I don't want to use the limit argument if you guys didn't discuss limits.
I don't think so.
Okay, then I won't talk about limits. But the rate of change, the instantaneous rate of change is getting really, really small, like average rates of change. And so part of the difficulty of this class is connecting all of the words and all of the math. Okay, So all of this means the same thing. And that differs from this average rate of change here. You guys remember how we found the average rate of change? By saying, like, if this is function f, so we'd take f of 7 minus f of 3 over 7 minus 3. And then that would give us some line with this as a slope, which is delta y over delta x. Do you guys remember that?
Yes.
Okay. So this is like just a general, this is like, it's still very relevant. The instantaneous rate of change is just when delta x is very small. So these things are very related, but depending on what numbers they give you, they can be very different. Like here we have a positive and a negative for the same like point. It's just the difference of like what's going on, like where is this point going? Okay, I think I beat that dead tortoise enough. Let's try, let's try number 8. Okay, so here we have the size S of a tumor in cubic millimeters is given by S is equal to 2t, where t is the number of months since the tumor is discovered. Give units with your answers. Okay, first of all, I would rewrite this as a function S of t is equal to 2t. So that way it's very explicitly stated that when t changes, the function s changes. That being said, what units are these all going to be in?
Cubic millimeters per month.
And then the t is given in months. So yeah, so if you look at like a graph and it looks like this, the units will be how many cubic millimeters does it change per month, because this one is in cubic millimeters and this one is in months. All right, that's good. Okay, so let's look at part A. Actually, I lied. We're only doing B and C. Let's look at part B then. What is the average rate of change in the size of the tumor during the first 6 months? How would I set this problem up?
With average rate of change, you would need to choose between 2 different points.
Yes.
Yeah.
And I'm given.
You want to know at 6 months, so you could maybe do like, I don't know, 4 months and 6 months?
Okay.
Sure.
I'm given the average rate of change for the whole first 6 months. So it wants me to go from 0 when the tumor is first discovered all the way up to 6. And it's going to be a line because it's an average. So Casey, what you would be finding is the instantaneous rate of change at approximately 6 months. But we're looking for the average rate of change over this whole time period. So we're just going to do S of 6 months minus S of 0 months all over 6 minus 0, because that's how we did our average rates of change. And this is something that they'll put on like quiz questions and stuff. They'll say something like, find the average rate of change for the first something. And then you'll be like panicking because like, oh, what's my other x value? I know I have to have an x that is at 6, but where is it from? And it's just 0. It's just from the very beginning. So S of 6 is equal to 2 to the 6, which is equal to what? 16 times 4. That's 48. That's not right. Sorry, I don't have a calculator on me. I should know this.
64.
64, okay. Minus s of 0, which is 2 to the 0. All, yes, all over 6. So 63 over 6. What does that mean? Like, so we have this, and we talked about the units already, and so this is the rate of change, and it's going to be in units, cubic millimeters per month. What does this look like on this graph up here that I kind of sketched out? Well, it's a positive slope, we know that, and we know it's a line because it's an average rate of change. And we know that for every 6 months, it goes up in size by 63 cubic millimeters. And so it literally just is the change in Y and the change in X. Okay, let's take a look at part C. Estimate the rate at which the tumor is growing at t equals 6.
I'm sorry to interrupt, but how do you know when not to? Because if I were to get that answer, 63 over 6, I would have immediately divided and gotten 10.5. When do you know not to finish
Honestly, I generally don't do that because on exams they don't give you calculators. So either they would have it in the form 63 over 6, or it would be 10.5, and I just didn't simplify it. Okay. Whatever you decide to do. I left it in this form in this instance because I wanted to compare delta y over delta x, but honestly, you do you. 10.5 is equal to this, and yeah, it works.
There was actually a problem in the first exam where it was like, okay, yeah, there were 2 possible answers, but you had to find the choice we gave you. I'm like, oh, okay. Cool.
Yeah, that doesn't seem right.
Yeah.
I don't like that. Especially if they don't give you calculators. That's like, if they gave you 2 right answers, you could contest that, is something I would say.
No, there was 2 possible answers, but in the choices, there was only 1 correct one. So
okay.
They gave you at the end is like, well, there was another option, but we only gave you these choices. So which other?
Yeah.
So.
Yeah. that's a dirty trick. I don't like that. But yeah, if you end up with an answer that's in a different form, just play around with it until you get the right form. If you need it in a decimal form, then do that like as much as you can. But it's just generally like I don't like that. I of course took all of my like tests on like paper, so they weren't like multiple choice. And so, like, the graders would have, like, all of these lists, but I don't know what they do when you take it through Examity, right? And it's, like, multiple choice on Canvas.
I've never taken an exam with Examity, but yes, we're all multiple choice right now.
Okay. All right.
Now, for part C, we do what Casey was saying, though. No,
exactly. Exactly. So we would take S of 6.01 minus S of 6 all over 6.01 minus 6. And I fished out a calculator, so we can do this. But in addition, we would also try S of 6.001 minus S of 6. And we can just keep getting smaller and smaller. So if you want to pick one of these to like put into your calculator,
so for because it would be for S 6.01, it would be 2 raised to 6.01 power.
Yep.
So 64.5 4, 4, 5, and it kind of keeps going, but.
Yeah.
And then for 6, we know that's 64.
Mm-hmm.
Yeah. And then be divided by 0.1.
Yep.
Which is a number.
It works out to be 4.451 or 4.452.
All right. So then we end up, like, we could do that, and then we could also try the one with, like, the more zeros in it.
I got 40. How did I get that? I got 44.5.
Oh, I missed one of my zeros. Sorry.
Oh, that's good. Okay, and this I ended up with 44.37. Okay. What is that telling us about, sorry, I'm trying to erase this, but my tabs keep popping up. Okay. So we have 44.52, 44.37. We could keep getting smaller and smaller and smaller and add more decimal points and more decimal points and more decimal points. But you can see that it's probably getting close to, I don't know, like maybe 44.25, maybe it's 44. We could figure out what exact number it's getting close to, but this is about what it is, about 44. Okay, this we said was 10.5. So what do you think the graph of at the instantaneous rate of change is 44? What do you think this graph actually looks like if it's not a line?
Wait, say that one more time. Sorry.
What do you think this graph actually looks like if it's not a line?
If it's not.
Because we know that this average is like just, it's something that we use to like make assumptions. This is referring to the slope here being 10.5. And we know that at this point, the slope is much closer to 44. So it's much steeper. So what do you think the rest of this graph would look like then? Not quite, Casey. Casey, the periodic functions, the ones that look like this, and then just keep going, they actually, when you take their derivatives, it looks something also very similar. It looks like this. So you can tell a periodic function like that. And also, this average rate of change is not the tangent line to this average is not the, trying to think of a good way to explain this. What we're looking at, actually, this is the tangent line. This is the one with the slope of 44. So, sorry, this was like a big ask. But it's just kind of like, I was just trying to like get you guys thinking about like what the graphs would actually look like if we had something moving like this. So we have a very steep slope that we know about. That's right here. We know that the average rate of change is 10.5 and it's moving up like that, for instance. That would mean that down here, the slope would have to be much less than 10.5. If this slope is going to be greater than 10.5. Because this is just like the average slope of the whole thing. And if this is greater, then this has to be less. And it's all going to average out to be 10.5 in the whole grand scheme of things. Between 0 and 6, that is. So that being said, we know that we have to have some kind of curvature. And that makes sense with the function that we're given, the 2 to the t, because we could like graph that out and we could say like, okay, so 2 to the 0 is 1, 2 to the 1 is 2, and then it would be like kind of like an exponential type function. And it would look like that, or something like that. I mean, it would just keep getting bigger and bigger. Okay. Does everyone understand kind of, number one, what I was asking for with that question? Because I don't think I was very clear. And number two, what I meant, like the purpose of that question?
The purpose was to find the instantaneous, the point, right? Where it's on 6.
Yeah. Yes, Casey, that's what I mean. Casey is saying that the average is not like what the actual function looks like, it's just connecting different points in the function. Okay.
That green curved line is what it would actually look like.
Yeah, something like that.
Yeah.
Is what we're assuming. I don't actually know, but yeah. A lot of this is just kind of like guesswork. Like you know something and you know something else, and so you try to put 2 and 2 together and see what happens. Okay, let's try problem 12. I'm going to clear all of that. Okay, so we were given this function. Sorry, my lines are, I can actually draw lines. Let me do that. We're given this function and we're asked to identify what points on the curve like belong to like what slope. So why don't you guys take a look and tell me what you think while I kind of sketch this out. Oh, hello, Rachel. We are on problem 12 in section 2.1.
Well, I feel like E has to be is the only point that's 0 because it's the only point that is 0.
Yep, you're right.
C is giving me a negative 3/5. Then F possibly for -1 because that's the only one that goes sort of negative. All A to B is positive, C to D is positive, E to F is the only negative.
Okay. So what we're thinking right now, you said E is 0. I should have color coded this differently. Sorry, I'm a big fan of color coding, but I do like a very poor job of it. F, D, C, B, and A. Okay. So you said that E was going to be 0.
Yes.
Okay. And you said that C was going to be -3. You said F was going to be -1. And D is going to be, did you give me that one?
I did not. I was
okay.
going to let other people give a shot.
Anybody else have any thoughts? That's a really bad looking 3. Oh, that's not 1. It's 1/2. 1 and 2. Okay. So, you did get E right. And you did a good job of identifying, you like process-wise, you did exactly what I would have done. You started off by saying, I know which one is 0, and that is E. And then there are only 2 points that have negative slopes, and those are C and F. You did get those mixed up, though. Why is that? It's because, like, right here, if you draw the tangent line, it's going to look kind of like this. And right here, if you draw the tangent line, it's going to look much steeper. So kind of just go through and draw the tangent lines is what I would recommend. But yeah, your process was very good. So here, this is actually F is -3, and C is actually -1. Okay. So now we have 3 more, and they're all positive slopes. Okay, we have 1 vote for A is 1/2 and D is 2. That would mean that B would end up being 1.
Which
and
does look steeper than B.
I would agree. And I would say that A is less steep than B. So I would say all of that's good. So here we have A, here we have B, and finally we have D. Okay. Personally, when I do these kind of problems with the graph and they're saying like rank the like all of this stuff, I go through and I draw out every single one of these tangent lines and I look at like how they compare to one another. And sometimes they're more right than others. Like for instance, my D could probably be angled a little bit more like this, but I like sketch them out to see what's going on. But yeah.
You just reminded me of a question I've been dying to ask. How do you know how to rank? So if someone were to then ask, rank these points, how would you even begin to
in terms of how large their derivatives are?
Yeah, I just ranked the values of the rate of change, and they really didn't give any actual value.
Yeah, that sounds like a gritty question. I don't like that. But what you would do is you would start with the ones that are the lowest. You'd say that the value of F, like the rate of change at F is less than C, is less than E, is less than A, is less than B, is less than D, if that's what they were asking for. Because this is the smallest rate of change and this is the largest rate of change.
Gotcha.
Yeah. If they're looking for like the absolute value of the rate of change, then that's just, I don't know, that's a weird question. But you would also kind of do it the same way. The absolute value would be E being the smallest, and then which is less than A, which is less than C, B, D, F. But I don't know when they would ask you that question.
Zero's in the middle because the negative, then the equal, and then positive.
Yeah, negative equals 0, positive. And here, if it's the absolute value, it's just like take away the negative sign and what do you have?
Okay.
So, yeah. I don't know when they would ask you a question like that, but if they do, that's what you do.
On the exam.
Ugh, that's such a gross question. Ugh. Okay. Would you guys like to talk about section 2.2?
Sure.
Cool. Okay. This is, honestly, this was like my least favorite. This whole, like, if I give you a graph of this function, please draw a derivative. Because I was just like, I got very confused very quickly doing this. So, I am gonna kind of jump if it's okay with you guys, I am going to kind of talk like very briefly about like something that you guys will be introduced to later, because later you're going to be like numerically saying like if my function f of x is equal to x squared, what is f prime of x? And so that's like a thing that you're going to be doing in, what is it, 2.4? No,
It's 2.5.
2.5, something like that.
They would give us a number for x, and then we would just have to do like the x. Do the 0.01 minus.
Yeah,
x.
but soon they're just going to be giving you something that looks like this, and you'll be able to find f prime. This is like coming up.
With no numbers.
With no numbers. And I promise you it's going to be a lot easier than you think it is. But the purpose of this is that these numbers relate very like specifically to the graphs. And that's something that I always felt like this book never really delved into enough, because my calculus teacher would always say algebraically it looks like this, and geographically it looks like this. Or graphically, not geographically. So algebraically we have this function for number 2 that looks something like this. And so it is like there's obviously like some changes there, but it is going to be some negative x squared function-ish. I'll write ish. So when you guys look at this, can you see the parabola?
Yes.
Okay, and you know that parabola equals x squared. So like a parabola, if you have a parabola function, you have an x squared. Like that is your main function. And you can like, it'll change depending on whatever's looking at it. But if you have a function that's a cubic function, it'll look something like that. And so all of these functions have very specific looks to them. And honestly, the easiest way for me to remember this is that f prime of something is like, it's just -1 for whatever you have. So f prime of this is going to be a line. F prime of this is going to be a parabola. Obviously, I'm just like sketching these out right now, and I have no idea how correct they are. But just kind of keep in mind as you like go through this that because this is x squared, its derivative is going to be x. And because this is x cubed, its derivative is going to be x squared. And you don't know those rules yet, and you don't have to know them for this section. It's just something that I find helpful to like think about them geographically. And something to keep in mind as you are learning more specifically what the derivative is. Obviously, I won't be asking you to like do that specifically right now. Instead, we're just going to kind of look at how this graph is changing and interpret how to find a derivative off of this. What do you think you guys would do first? Yeah, I know. Okay. The question is, we're graphing the derivative of the functions. So we're given this, and this is like a function. So what's the derivative? Yes. Graph the 0 point first. I like it. Exactly what I would do. I'd say this is where f prime is equal to 0. And then I'm going to go set up my f prime graph. And it goes at this x value, whatever this x is. It's like right about here-ish. So this is where f prime is equal to 0. Because the x values are going to be the same for each of these graphs, it's the y values that are going to be different. Okay, then what would you do? Okay, I divvy it up. I say, okay, so here It is positive. Yep. If it's decreasing or increasing, exactly, Casey. So here, I know that it's increasing. The derivative is positive, and it starts off very positive and becomes less positive until it gets to 0. So here, the derivative is above 0. So this is like the positive region. Then I'm going to go one step over here, and I'm going to say this is negative. And it starts off kind of like small negative, and then it gets very negative. So this is my negative region. So basically what it's saying is that the numerical value of whatever this derivative is going to correspond to whatever the y value is on this graph. If, for instance, here f prime was equal to, I don't know, like 1/2, then here this is 1/2. And here, if it's equal to 2, then here is 2. Because this point on the x corresponds to one another, and this point is on y. I don't know why I drew that there. Anyway, does that make sense as to like how this happened?
Because derivative is instantaneous.
Yeah. So what? Yeah. Consider when you're drawing this, this is actually a when you're like graphing this. This is the x-axis, and this is the f prime of x axis. So whatever f prime of x is over here, it goes directly as the y value over here. So if x is equal, here, let's try, like, I'm going to pick a brighter color so that you can see it. Actually, this is a really ugly color, but we're going to do it anyway. Okay, so here x is equal to 0. And I'm going to say that this slope, I'm just going to guesstimate. And this is not, you wouldn't numerically quantify any of this when you're doing a problem like this. I'm just trying to like explain a little bit better. F prime here is equal to 3/4. So I know that f prime is equal to 3/4. So my point, x f prime of x, would be 0, 3/4. And so I go here and I say, okay, so my x value is 0, my y value is 3/4. So I go 0 over and I go 3/4 up. And so this point is 0, 3/4. So whatever this f prime is, it gets put onto the y-axis here. Thoughts? No one has any thoughts about this? Yeah.
Just so we're, this was problem number 2 on point 2.2.
Yeah.
Even though we didn't even care about that, the 4y or the 4x, like that was just background noise. Like
I mean, to me, it is just background information.
We didn't have to find.
Yeah, I considered it background information because I think it's more important that you're capable of recognizing that if I have a function that looks like this, when I take its derivative, it's going to look more like this. It's going to be a line. And that is a tip. If you see a parabolic function, guaranteed its derivative is going to be a line. So if you see anything that looks like this, if there's just one little hump, it's going to be a line.
But then if it's multiple humps.
Yeah, then it gets a little bit different.
Yeah.
Okay. So yeah, I like conceptually, I think that like being able to like look at this and saying like, okay, say like, okay, I like understand how to get from like this graph to this graph is more important than saying this is equal to 4. But I'm going to redraw this and we're going to look at the numbers, and this is at -1, -1. This is at 1, 2. Oh no, 0, 2. 3, 3. No, 1, 3. 2, 2. And -1, 3. So these are, this is 1, 3, 2, 2, 3, -1, -1, -1, and 0, 2. Okay, so that being said, like I have all of this stuff. Given this information, you can graph the derivative, because first of all, we know that the derivative f prime is equal to 0 when x is equal to 1. So I'm going to draw a big dot here. And then, I mean, like, you could go through and do your, like, calculations, like, f of -1.0001 minus f of -1, and then, like, dot, 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 like, do that whole thing. But I think the most important thing is being able to pick out, like, this is where the 0 is. At point 0, the derivative is smaller or less positive than it is at point -1. And so with the numbers in there, I would still just draw something that looks like this. What if the graph looks like it stays on the 0 point? Casey, are you talking about a graph that kind of looks like this? Or are you talking about a graph that looks like this? Second one, okay. If you were to have a graph that looks like this, what you would do is you'd say, okay, so here is the section where my derivative is equal to 0. Here is the section where my derivative is positive, i.e. it's going up. And here is the section where my derivative is negative, i.e. it's going down. The slope is negative. Okay, so you would set it up exactly like we just set up this problem. We'd say, all right, this is point 1, and this is point 3. And so we know from point 1 to point 3, the derivative is equal to 0. So it just equals 0 for this whole time. We know from this, I drew it as a line, so it's just one constant. Let's say this slope is 1. So it would look like this. Because I drew it as a line. And then this slope is going to be -1. The slope of this line all the way down, because I drew these to be linear, it would be -1. Okay. And obviously this would be weird because there is no like transition. Like this would make it like not a function because you have these lines here, because you're immediately going like at one point you go from all the way like your derivative is positive and then your derivative is 0 from that point on and your derivative is negative. But because I drew it as a line, that's what it would look like. If, for instance, it looked like this and was curved and then it got flat and then curved down, then you would have more of you would have like a line coming like that and then a line coming like that. But you just have this flat area here is the point. Okay. All right, let's try number 4. So we have this graph. It looks nasty. What I would remind you is that what you will learn later is that when you take the derivative of a periodic function like this one, oh, I should move this line. The result is going to be another periodic function. So you know that this graph, when you take its derivative, is just going to end up looking like a periodic function again. Right now because I'm telling you, but in the future because you'll be able to tell yourself. Okay. So it looks something like this. All right. Who wants to start? First thing we do?
Find the 0.
Exactly.
But now, could there be 2 0 points?
There are exactly 2 0 points. Oh, that's not what I need. Okay, cool. There we go. 0 and 0. And if we were being very precise, this is at like 3.5, negative 3.5, and this is at, I don't know, 1.5, something like that. My graph is clearly not quite to scale. But like I said, I think conceptually it matters more that you're able to say this is where the zeros are. So that's what I would focus on. Okay. Okay, then let's start by asking ourselves, where is it positive? Where is the slope going to be positive? So the slope is going to be positive in this area. And it's going to start off as a small positive, and then it's going to end at a small positive. Because it starts off from 0 and then approaches 0. But this point in the middle is going to be a large positive. So what is that going to look like? Well, we're going to start off with something that's like up in this positive region, but it's like not very positive, and we're going to end with something that looks the same. And then we're going to have something in the middle that looks more positive. So you're just going to kind of connect it. And that's how I think about the process. Like, ask yourself, where is it the least positive? Where is it the most positive? And connect it like that. That being said, because you know it's going to look like a periodic function, you can also kind of link it there. Okay, it's negative in these other areas. It's coming down like this. It's more negative, less negative. From here, it is less negative to more negative. So it's going to be less negative here, and then more negative down there. And it's going to be less negative and then more negative. So yeah, that's what it looks like.
So could we do number 6?
Yeah, for sure. Sorry, my graph drawing is not the highlight of my, I don't know, artistic abilities.
Great.
Especially on Zoom. Okay.
But it's like that entire flat part, that's 0.
Yep, it is.
Cool.
Um,
The point, of course, not bug.
Oftentimes, it's good, like you're gonna see something and you're like, oh no, like what could this possibly be? But it's gonna be like exactly what it logically seems like it should be. Okay, so this is our original function, and I'm gonna draw it in black. Okay, this 0 portion is gonna curve down, and it's gonna come back up. Sorry, my tablet is not big enough to do this whole thing at one go. We're gonna get the flat area, and then it's gonna come back up. Okay. We start off with asking where our zeros are. And we already said that this whole thing, it's flat, it's gonna be 0. So I'm just gonna make that 0 down here. And then, is there any other places where it's 0?
Yeah, on the bottom, yeah, right there.
Okay.
It's like what, quadrant 2? I forgot about that.
Yeah, no, it's 4. It goes 1, 2, 3, 4. Yeah, that's been a hot minute since I've done that. Okay. All right, positive. Where is it going to be positive?
From that point you just put going up is positive.
Where is it the most positive? Is if this is at what? This is at like 3, and this is 4. Is it more positive at like 3.5 or at 4?
4.
Okay. Less positive at like 3.5. So we're going to draw something that kind of looks like this. Okay. Where is it negative?
Everywhere else.
Yep. Okay, so we're going to have this being negative. Is it more negative here or here?
Closer to the bottom, towards 0.
Actually, this slope is more steep, and it kind of tapers down as you get down. So more and then less. So it's more negative and it's approaching less negative. Another way to like think about it is that if you tried to graph this as this being more than this, you could not connect to the 0 because it would look like this. And then you just like have to like jump up to the 0. And because the instance that I showed you earlier was like a little bit of like a unique kind of thing, and you don't usually do something like that. Okay, so we hit that point. Next we need to ask about here. This is not very negative. This is pretty negative. And then this is less negative. Do you know what I mean by when I say like less negative? What I'm like trying to imply that the absolute value of whatever number is in here is less than the absolute value of this. So for here at like 0.1, let's call it, and then here at 0.2, the derivative here is much steeper in the negative direction, so the absolute value of it is going to be greater. Make sense? So it's going to look like this. It starts off less negative, gets more negative, it reaches a point where it's coming back up and becoming less negative, and it looks something like that. And so this is like a very choppy like way of graphing it. In reality, the graph is going to look a little bit more streamlined than the way that I drew it in these chunks. It's going to look something a little bit more like that. Okay. Just for future reference, in terms of, okay, like next section 2.4, we're talking about the second derivative. This is, like, if we were to take the derivative of this, where it's 0 here, this is the second derivative. So that's just something to keep in mind as you move forward in the week. How are you guys feeling about this? Cool. We have one person who says it makes sense.
Yeah, it makes sense.
Cool.
Yeah, it makes a lot.
It's like my least favorite part, and I literally have to do this so slowly. Like, yes, I can, Casey. Let me do that. Let me figure out what we're doing there. Okay. Casey, are you talking about a problem like maybe 23? Did I ask you guys, do you guys do homework that you turn in?
No.
Okay, so any problems for a game. That's good. That's good to know. Okay.
And it's sort of like this, the problems in the book, they give you the answers, yes, but if you don't know how to
get to them, you're like, yeah. How did you do this?
Yeah.
Yeah. Okay, so value is 23. Yeah, okay. Values of x and g of x are given in the table. For what value of x does g prime of x appear to be closest to 3? Okay. So we're going to think about this in terms of how I would solve this, at least, is I would look at this and I'd say, oh, sorry, we're doing 23. I would look at it and say g of, gosh, 2.7, or why would I start with 2.7? That would be a foolish thing to do. 3.2 minus g of 2.7 all over 4.4 minus 3.4. That's a lie. I messed that up. So I can't erase this fast enough. It's fine. Just don't look at that. I messed it up. Okay, it's just 2.7 minus 3.2. I cannot. I'm sorry. It's been a long week. You guys know how to find averages. I know you do. And I hope you don't listen to me ever. Okay.
Yeah.
There we go. That's what it looks like. So then it's going to turn out to be 3.4 minus 4.4 over this, which is approximately, what, 0.5? So it's going to be 1 over 0.5, which is, did we talk about this last week when I said I did something like jumping the fence? If it's 1 over 1/2, it is equal to 2. Because what you're going to do is you're going to multiply both top and bottom by 2. And you're going to end up with, 2 over 1. Okay, so this is approximately 2. All right, so now that I have like a general idea of like what's going on here, I'm going to look, let's see, each time x increases, it's going up by 0.5. So I am going to look for something where I'm just going to call this delta g of x over 1/2 is equal to 3. I'm like reverse engineering this problem so that I don't have to do it one at a time. Doing it one at a time is a completely viable option, but it's just time consuming. So what I would do is I would say, all right, so I'm going to multiply this by 1/2, and then I'm going to multiply this by 1/2, and so these 2's will cancel, and this is going to be delta G of x over 1 is equal to 3/2. And so I can get rid of this 1, and so I know I'm looking for something that is approximately equal to 3/2. Okay, now I can go back and look, which is equal to 1.5, right? So now I can go back and look at my g of x, and I can say, okay, for instance, if I have g of 4.2 and g of 3.7, my delta g is going to be 0.4, which is nothing like what I need. So I'm going to go and I'm going to just kind of keep looking. What jumps out to me is I see g of 5.7 and g of 5.2, and that looks like it's going to be a delta g of 9.0 minus 7.4, or that is an increase of 1.6, which I think is pretty darn close to 1.5. So I'm going to say the point at which, so here what we've established is that the average rate of change between x is equal to 5.2 and x is equal to 5.7 is equal to 1.6 over 1/2, which is it's gonna pop back up, and it's gonna be close to 3. It's gonna be 3.2. So I'm gonna say that that's about where it is. That's what I want to look for. And honestly, I think they would accept any answer between 5.2 and 5.7. So the value of x, where g of x appears to be closest to 3, is 5.2, 5.7, something like that. I would go with 5.2 because that's like where it starts, and the line would kind of go like that. But I would just say 5.2. How I did that make sense?
Yes.
Cool. Like I said, doing it one at a time is totally fine, but it would just be time consuming. If it asks for something close to x, yeah, I mean, especially right now when you guys don't have like the experience in like looking at like this function and then saying, oh, the derivative of that is obviously this. I would just use average rate of change and like get as small as you can given the numbers that you're given, and you can make assumptions from there. For instance, if the average rate of change from these 2 points is 5.2, then that's the closest you're going to get to what the derivative actually is. So, like especially right now, just try to get it as small as you can, obviously, but it's totally reasonable to do something like this and use average rate of change to solve the problem. Cool. Okay, do you guys want to do, do you guys want to move on to 2.3, or do you want to do more in 2.2?
Mm-hmm.
2.3? Going once, going twice? Okay. All right. All right. So we are going to start with problem 2. We are going to, the cost C of a steak in dollars is a function of the weight W of the steak in pounds. And so it's asking us to write, number 1, the Leibniz notation for the derivative of the function and include the units. Leibniz notation, this is another one of those things where it's like, what do you do when you're given words and you're given like this mathy stuff? So I'm going to remind you that instantaneous rate of change is equal to derivative is equal to f prime of x is equal to df dx. And Leibniz notation is this one. So one way to think about this is it's kind of like delta y over delta x. It's not, but it's like if you're having a tough time like remembering which one it is, then kind of think of this. Okay. Also, you don't get to separate these. You don't get to like multiply two sides by dx to turn it into like just df. Like consider this like one unit that you don't get to separate. Okay. So I would start by asking myself what the original function is. So I would start, what is my dependent variable? Any ideas? Okay, so my dependent variable is the one that's going to change in response to the independent variable, and the independent variable is not going to change. Okay, so weight is going to be my independent variable. I can manipulate weight, and if I manipulate weight, it changes the cost. So it's going to be C of W is equal to some function of W. Okay. So now that I know that if I change the weight, then I will change the cost. Okay. So the derivative of this could be written C prime of W, but because we are writing it in the form of Leibniz notation, it will be dC dW. So when there's a change in weight, it changes the cost, is basically what this is telling us. Okay. And the units are going to be just like if we had it as delta y over delta x. It's going to be dollars per pound. No, it's going to be pounds per dollar, I think. Why did I do that? Yes, it does matter which one is on the top and bottom. The independent variable is always going to be on the bottom. And the way I kind of remember that is dy dx. If I have a generic graph with x as the x-axis and y as the y-axis, then it's going to be, or y is equaling f of x. So y is dependent on x. So if you change the variable on the bottom, then the top one will change, yes. So I kind of like always refer back to this to like just make sure that I'm like on top of like making sure I know what it is I'm talking about. Okay. So what is the change? What is the units? Is it dollars per pound or pounds per dollar? Okay. Dollars per pound, we have a vote for. I agree with you. But I'm like questioning myself right now, and I'm not sure why. So give me a sec to like think about this. Yeah, it's just pounds or dollars per pound. Okay. Ignore me not being on top of this. Okay. Cool. All right, let's try number 4. You guys tell me what you think about this. So we have an employee's pay, P, in dollars for a week is a function of the hours of worked, H. So what's my function going to be? My original function.
It's P of H.
P of H.
Mm-hmm.
Exactly. Okay. So now I know I need to find P prime of H, or is it going to be DHDP or DPDH?
DPDH.
PDH. Exactly. Whatever inside here is going to go on the bottom because that is the independent variable. Okay, so DPDH, and that's going to be in terms of
B.
units are
Dollars per hour.
Yep. All right. So that's that. Let's talk about number 6 now. Okay, so this has 2 parts. An economist is interested in how the price of a certain item affects its sales. At the price P, a quantity Q of each item is sold. We have Q is equal to F of P, or how I would say it, I would say Q like of P, because it's just like it's a function that depends on P. Q, what this is saying is that Q is dependent. That's all they're trying to tell you with this. Explain the meaning of each of the following statements. So we're given F of 150 is equal to 2,000. Which also, because we're given that F of P is Q, this is also Q. And then we also know that Q is equal to F of, or excuse me, F prime, that's not Q. We're also given, oops, okay, F prime of 150 is equal to negative 25. Okay, what does this mean?
It means that, would it be at 150? At 2,000 quantity, it's 150?
It's the reverse of that. When the price is equal to 150, you sell 2,000. So this is the quantity sold. So when price is equal to 150, you sell 2,000 units. Does that make sense?
Yeah.
Okay. Okay. So if I'm looking at F prime of 150, now what am I looking at?
When you've made exactly $150?
This is price. So this isn't money that you're earning, it's products that you're selling.
So
Lose 125? I mean 25? Negative 25?
Keep in mind, so, okay, so here we have Q, and this is the rate of change of F, which is also the rate of change of Q. So the rate of change of Q is negative when the price is equal to $150. So if we took this from $150 to making it $151, if we charge them for the same item, you would sell 25 less items. So every time, like, or at least at this specific moment, if you moved it from $150 to $151, you'd sell 25 fewer items. But if you lowered the price, then you would probably gain more items sold. So this is kind of like exploring the relationship between like how much something costs and how much something that you can sell it for. Okay, so the rate of change of Q at this particular moment, if you were to increase the price, would be negative. So you'd lose customers. This is something that I like to talk about a lot, especially because this is like business calc. Are all of you guys business majors?
Yes.
Okay. So this is like conceptually like something that you understand. I'm sure, like if you increase the price, fewer people will buy. And it's just trying to like put that in like mathematical terms. Personally, I would have disregarded the whole F of P from this problem. I would have written the problem a lot more like this. Yada, yada, yada. And then I would say that the quantity when something costs $150 is 200 or 2,000, excuse me, and the rate of change of the quantity is negative 25. I don't know why they included the F in there. I just think it makes things more confusing, which is the last thing you need right now. So I look at this in terms specifically of Q is quantity. Q is going down if F goes up. And that is what the derivative like is referring to. I had a question, I think, earlier this week about, well, if this goes down, then you'll sell more. So isn't the derivative positive? But what happens is we ask ourselves when we're considering derivatives, if X increases, what happens? So if X increases, if we move from 150 to 151, then Q is going to go down. So that's the relationship between them. You guys are very quiet, and I don't know if you're like thinking very hard about this or.
I'm at a loss with that last one, but I just don't understand it. Do you mind explaining it again for me, please?
We are gonna rewrite this one. This last one being number 6, right?
Yes. Part B.
Okay. Yeah. Okay. Okay. So we're gonna rewrite it in a way that I think is more comfortable for thinking about things. Keeping in mind, of course, that you can do whatever the heck you want with these numbers as long as it like, is like within reason. So if they tell you that Q is equal to F of P, I see no reason why it can't be Q of P. Is everybody good with this?
Yes.
Okay, so we cut out the F. We don't need that anymore in our lives. We have part A. We understand that when Q of 150 equals 2,000, that we're selling 2,000 units.
Yeah, I understand that part.
Okay. Sorry, I just want to like rewrite the foundation of what we've got. Okay. Then we come to Q prime. So what we talk about when we talk about a derivative is rate of change, obviously. So this is how does the quantity sold change if price changes? So that's kind of the question that this Q prime is asking. And this Q prime also wants to provide the answer. So if we ask this question, how does the quantity of items sold change if the price changes? We have our answer in the form of this equals. So this is like a question and this is like an answer. If
Okay.
the price goes up, and this will always go up when you're thinking about this, you're like, it's kind of like, it's like an assumed part. This question here, how does the quantity sold change if the price changes, is always if the price goes up, or if this rises, if this goes from $150 to $150.50, or $151. Not entirely sure, but we know that if the price were to go up, then the quantity sold would go down, given by this negative sign, and it would go down by 25 units.
So if there wasn't a negative sign there, that would mean that the sales would go up 25?
Yep. And so we could assume that Q of 151 is equal to 2,025. As it is, we're assuming if positive.
Okay.
As it is, we're assuming the Q of 151 to be 1,975.
Yes.
So, okay, so why does it go up? G prime is the relationship with the result if it's going up, increasing. Okay, Casey, I'm not sure if I get your question. It's not Q prime that's going up, it's the price. And so it's like an assumption that we make as, like, when we're looking at a problem. We're never going to say if Q is equal to, okay, this is a different problem, so I'm just going to use completely different, I don't want to, like, confuse you guys by using the same variables, so I'm going to use different variables, if that's okay. I am going to say if f of 20 is equal to, I don't know, 15. And then f prime of 20 is equal to 3. So what this is telling me is that if I take f of 21, then I'm going to assume it's going to be close to 18, because it's what f of 20 is plus the change. So we're expecting, this is what we're saying, is that we're expecting f to rise if this goes up. But we always have to make the assumption that this is going up. We can never say that f of 19, for instance, if this, like, internal part decreases, we can never say that f of 19 is going to be 18, because I'm trying to explain this. I got a question earlier this week from a student talking about a problem on the quiz, and I think it would be helpful to talk about that here. Okay, do you guys remember the one with the cost of heating a home? It should have been on, like, quiz 1, I think. And you were given something that looks kind of like this. The cost of heating a home is dependent on the temperature outside.
Oh, I didn't see that one.
Okay. It may not have been on all of the quizzes. I guess I'm not sure. But so the cost of heating a home is dependent on the temperature outside. The cost of heating the home when it's 20 degrees is $22 a month. I don't know what the units are. But the issue that this student was running into is that they were saying that if the temperature were to go down, the cost of heating would increase. So if this is my temperature, and that's a really poor graph. Of course, would recommend thinking about this in terms of graphs. If this is my temperature and this is my cost, they were saying that, okay, so here I am at 20, and my cost is 22. If I were to change this and say my temperature is now 10, which is over here, my cost would be significantly higher. And so they were thinking about they were thinking about this, but they were saying that, okay, if I change this to C of 10, then my cost is going to go up. So the derivative should be positive, right? But the issue is that we have to think about this as increasing. I'm like, it's just kind of like an assumed norm that it means going up. So we think about it as C going to 21, C going to 22, C going to 30. And if the temperature does rise, then the cost will go down, so the derivative is actually negative. Because thinking about it in this terms is correct, absolutely. But because the student was thinking about like cost decreasing, or temperature decreasing and cost increasing, everything got switched up around. So you have to be sure that when you think about Q of 150, you're not thinking about what happens if Q, if I take Q of 140 or Q of 100. What you need to think about is, what do I do when I take Q of 151? And that's what this is telling you. You have to make this go up to 151 or 152. Whatever it is, it's rising. Are we cool with that? That's what I was like trying to communicate.
Yes.
Okay. So you're never going to say if Q prime of 150 is equal to negative 25, then Q of 149 is going to be, and then like use this as like something, as like a method, like subtract 25 from whatever you have, because it is, you have to like make sure that this part is becoming greater. It's moving up the x-axis. That's a really bad x. Okay. I'm sorry for all of that confusion. I did not mean to make that confusing. Okay. Is everybody feeling better about that, like conceptually now? Like how?
Yeah, it's like,
Okay.
you explained it much better this time.
Yeah.
Okay. All right. Does anyone have any more questions about this section? Give you guys a few seconds to look over.
Can we do question 9?
Okay. Okay, so when you breathe, a muscle called the diaphragm reduces the pressure around your lungs and they expand to fill with air. The table shows the volume of a lung as a function of the reduction in pressure from the diaphragm. Pneumologists define the compliance of the lung as the derivative of this function. Okay, so basically we have this function that is, let's see, volume of the lung. Hang on, my phone is yelling at me. My phone's like audio recognition is like severely broken and it always thinks I'm talking to it. It's the saddest thing. Okay. So we have this function that is the volume of the lung that depends on the reduction in pressure. So I'm going to call this P, but it's not actually P. It's pressure reduction. So as the pressure decreases, P is actually going to increase. Is that okay with everyone? So P is equal to beginning pressure minus end pressure, and end is less than beginning. So P is going to be positive, even as the pressure is decreasing. Okay, so we've established that. What are the units of compliance? We know that compliance, as defined here, is equal to V prime of P. And we know that volume is in liters, and our P, pressure reduction, is in centimeters of water. Okay. So let's try writing this in Leibniz notation. How would I write this in Leibniz notation?
dV over dP.
Yep. So my units would be for every change in centimeter of H2O of pressure reduction, I guess is the units that they're using for pressure reduction, the volume would increase. I don't think this is right. Give me a sec. Let's look this over. Okay, yes. This is the units, but it's not exactly 1 liter per 1 centimeter of pressure reduction. What it is, it's going to be, so these are the units, liter over centimeters, but what it is it's going to be, it's like the slope. Like if it was like a line, it would be something like closer to, like what we're finding is 0.2 liters. That's a lie. 0.29 liters over 5 centimeters. Minus, okay, if that's not a 0, that's not a 2, that's a 0. So it would change by approximately 0.1 liters per 5 centimeters. According to like the first piece of data that we found. So that was just like the average rate of change starting at the beginning. So this is the units, but it doesn't, sorry, I got confused at the beginning. This is the units, but it doesn't equate to 1 liter per 1 centimeter. This is a rate of change, and that's what we're trying to find. Okay. That being said, now that I've thoroughly confused myself and all of you, so we have the units of compliance. We're estimating the maximum compliance of the lung. Okay. So how would we go about doing this? How do we get maximum compliance? Compliance is, how do we get the largest ones? Largest V prime of P. Well, because we know they have a positive relationship, we know that as pressure is reduced, the volume of the lung goes up. So we want
the highest, like 30 and 1.
Yep. So looking at like the table that they give us, if P is equal to 30, then the volume is equal to 1, so 1 liter. So volume is going up as P is going up. So what we want to get the largest, oh, this is not, I lied. Okay, so this table is talking about V versus P, and we need to be considering V prime versus P. So we want the largest V prime of P, which is the greatest rate of change between things. Does that make sense? Because what we're looking at is V prime of P, not V of P.
So then we would, you would still start at 0.0 and, right? Because you're
okay.
No.
Give me a sec. Casey, it's just called compliance. It's like the word that they use to describe it. What they want you to do is just consider. Yep. Okay. All right. So in order to get the greatest compliance, we want the largest V prime, which in terms of what we have a table, we need the greatest rate of change. Where do we get that? I would look at the table and I see that it's increasing every 5 centimeters. So I would look for the greatest increase in volume over 5 centimeters of water increase. And to me, that looks like it's between 10 and 15. It goes from 0.49 centimeters to 0.7 centimeters. Or not centimeters, liters, excuse me. Whew. Bad. Get units right. And so that would be 0.7 minus 0.49. 1.2, 0.21 divided by 5. So this seems to be the biggest rate of change given by this table. Would everyone agree with me? Because this is the biggest shift in liters given by a shift of 5 centimeters of water. I think the units are what's making this particularly difficult.
Yeah, no, because what you're saying is between 10 and 15, if you subtract 7.70 minus 0.49, that's the most that it's done in between.
Yes, that's exactly what I'm saying. I abbreviated it a lot, but that's exactly what I'm doing. I'm finding an average rate of change. Okay. That being said, we are trying to find the maximum rate of change. So that would be, I don't know, somewhere between 10 and 15, probably closer to 10. For B, I'm just going to say approximately at 10 cm. So the largest V prime of P would be V prime of 10. But we don't have a function, so we can't really, I mean, like it would be approximately this. Whatever this is. You could divide it out. But I would just take this as my answer because I don't have the time to I don't know, deal with what the actual number is. Okay, so explain why the compliance gets small when the lung is nearly full. And so it gets full at about 1 liter. So the compliance is getting small. I would think about this in terms of a graph, actually. So we start off kind of going slowly, and then all of a sudden we hit this like big compliance. We hit this big compliance, and then we come back down, right? So the graph kind of looks like this. Start off slow, we hit max compliance, and then it comes back down. And that's what they're kind of telling us. So this is the graph of the derivative. This is the graph of V of P. And it's going to look something like, let's see, that is, does it look something like this? I think so. I told you guys earlier, like, getting graphs from other graphs is like my weakest point in this whole calculus experience. So if I take this, this is small positive, big positive, less positive. Yeah, this is what it's going to look like, something like that. Kind of like an S curve. So we notice here that the fuller our lungs get, this is volume in liters. The smaller the rate of change of the compliance gets. And the reason that is because our lungs are getting full. So we're able to, like, every change in pressure is not as like impactful on the amount of stuff we can hold in our lungs. It's like we're approaching our limits. We can't get any more air in there, no matter how much we reduce the pressure. It's just straining our lungs. And so mathematically speaking, when we're explaining why the compliance gets small when the lung is nearly full, we can see that the derivative, it has its maximum value right here at the top, which is this maximum compliance here. And this is somewhere around, I don't know, 10 to 15. And then this, when the lung gets full, it gets to the point where, like, no matter, like, if you were to reduce the pressure more, you just couldn't fit more air in there. So we hit this point on here. So this is 10 to like 15. We'll just call it 10. And this is 30. And you can increase or reduce the pressure as much as you want. This is a straight line. This is not going anywhere. This is going to be a straight line. No matter, like, you can get down to 60 centimeters of pressure reduction, and it's like you just can't fit any more in your lungs. You've hit the limit of what your lungs can manage. Does that make sense? Okay, I have one person who said yes.
Yes, I keep reading on mute, sorry.
Oh yeah, no, you're good. Okay. We're hitting about 1 o'clock. If there are no more questions, I think it's about time to wrap it up, if that's okay.
Thank you very much.
Thank you guys for coming.
Thank you.
Feel free to email me if you need any help. I've got a couple exams this week, but I should be checking my email like all the time to like check out when things are happening.
Just to confirm though, we're going to be doing this every Sunday, and we can just follow the link because I didn't see an email.
Yeah, the link should be. I put that announcement out that said like, oh, here's like the link because the first one got screwed up. There should be a link that is public also in Canvas now, like right beneath like the other links to Zoom rooms.
Yeah, it's underneath Kasha's room. It's working now. Last week it wasn't.
Okay.
Gotcha.
Awesome. And I was just about to say something about like where the videos will appear, but like you guys are already here, so you probably won't watch the videos, and the people who need to know that information can't get it from the video if they can't find it. So I'm probably not going to say anything, I guess. I'll just post like an announcement about the video.
Well, thank you very much, and everybody enjoy their Super Bowl Sunday.
Yes. Everyone have a great day.
Okay, thank you. Bye.
Bye.
Thank you.